temperature anomaly observed in the Semipalatinsk test site area. Snow cover is absent in this region in winter, and the surface temperature was higher than surrounding area, about 10 degrees by Celsius. Area of thermal anomaly is nearly 3 times larger than Semipalatinsk test site area. Abnormally strong attenuation S wave observed at depths of 10 to 120 kilometers in the Balapan area, where two large fault zones located. Attenuation in the Degland area is much weaker in these depths. Q factor sharply increases in the depths greater than 200 kilometers in the test site region. This figure shows general S-Coda envelopes constructed from the record of calibration explosion conducted in 1997 at the Balapan site, and Coda envelopes constructed from the record of explosion conducted in 2005 to 2021 in the Karajira quarry for station S9 and Balapan 2 located in the same area. And this figure shows attenuation field section by data with S9 and Balapan 2. These figures show Coda envelope and attenuation field section for another station located in the Balapan site. Another example, and this slide shows mapping of attenuation field heterogeneities for the lower crust of Semipalatinsk test site area and for uppermost mantle. Attenuation field heterogeneities mapping done for lower crust and uppermost mantle in the east of Kazakhstan. Very low Q factor values correspond to several stations installed in the area Balapan test site, where the most powerful underground nuclear explosion were conducted. The research considers the spatial-temporal variation of short-period shear wave attenuation field in the East Kazakhstan lithosphere, including the region of Semipalatinsk test site, where a lot of underground nuclear explosion conducted in the past. Big temporal variation of the attenuation field in the Semipalatinsk test site region were found using data of distant station recorded underground nuclear explosion and quarry blast. The common S-wave Coda envelopes obtained by records of close calibration and mining explosion, as well as local earthquakes by data of 20 permanent and temporary stations. Obtained data allow to create attenuation field section in the lithosphere of considered region. Attenuation field heterogeneities mapping done for lower crust and uppermost mantle of the East Kazakhstan. Very low Q factor values correspond to several stations installed at the area of Balapan test site where most powerful explosion were conducted. These values are lower than minimum values correspond to large number of stations installed in the seismic active region of northern Tingshan. It's supposed that effect is due to uplift deep sea fluids along active fault zone under the long intensive vibration effect. According to our data, zone of high attenuation of S-wave in the region of Balapan site could extend to depths of 150 kilometers. Earlier, we have found similar spatial-temporal variation in the attenuation field structure in the region of other two largest nuclear test sites, Nevada and Livermore. Thus, a long-term intensive man-made impact in the geological environment can lead to significant change in the characteristic up to sufficiently large depths not only in Earth's crust, but also in uppermost mantle. Thank you for your attention.
Thank you very much. I can take one question. Is there any question? I don't see an online question, so also online participants can use the mobile app to enter questions in the Q&A part of the session. No questions from the audience, so thank you very much, Anna.
Thank you.
So the next presentation will be by Amanda Price from, I think, Lawrence Livermore National Laboratory, if I'm correct, I'm sorry. It's about historical nuclear tests and collapse data from the Livermore National Network between 1997 and 1992. Yes. Thank you very much. Please.
Great, thank you so much. So again, I'm Amanda Price. I'm a seismic data manager and data specialist at Lawrence Livermore National Lab. Today I'm going to talk about some of the work me and my colleague Rebecca Rod have done looking at some of the historical data that we have for nuclear tests as well as the associated collapses. So I think this is a problem that we know here. The data is rare. It's a success that we don't have modern data to compare to. This is a limited data set, and we have retiring personnel and lost metadata that makes this an even bigger problem. Both me and Rebecca Rod are early career scientists, so it's a great opportunity for us to start to learn some of these methods and try to recover the data and learn how the technology has worked and how we can correct for it. So the Livermore National Network is a unique opportunity that we have. So just a little bit about the Lawrence Livermore Nevada Network or National Network. It's been rebranded several times. It is 4 analog broadband stations that were started to deploy in the 1960s. So here I have a map of those 4 stations. In the middle, you can actually see the outline of the Nevada test site or the Nevada National Security Site. And then we have a good azimuthal coverage. To the north, we have ELCO or ELK, which has been adopted into an auxiliary seismic station. The MNV to the west is MINA, and that is adopted into ENVAR, the array, a primary seismic station. To the east is KNAB, KNB, which is still operating under the UU network. And to the south is LAC, and unfortunately that one did close in 1999 due to vandalism. It was hard to maintain. So we have a great data set here. The problem is that we need to be able to validate the data that we have. So just a little bit more about the LNN, as I'll refer to it. This is kind of the timeline of the network. It started off in analog FM tapes, a one broadband vertical array channel. In 1976, we started to have 3 broadband components, but it was still analog, continuous data. In 1979, it became a digital telemetered network, but it was event detection only, so we lost our continuous records there. But in 1980, we went back to our continuous records. So from 1980 on, we do have continuous digital data. And then in 1988, we actually have now 6 components. We have 3 broadband and then 3 high frequency channels. So that's just a little bit about the network itself. So one of the issues that we have is that, okay, let me back up. There has been some data that has been released from the LNN. We identified 108 events that were previously unreleased. In this, we actually manually QC'd them. We found dead channels. We looked for non-seismic noise, spiking, gap, and timing issues. We did this manually. Here I've just plotted up where those events took place. In the outline here, you can see we have quite a few in the eastern side of the test site. I've colored it by depth of aerial just to give you some kind of idea of the range of events that we have. And then on the west side, we have kind of the deeper buried events. I also have a timeline of the number of events that we have. You can see most of them are bracketed between 1979 and 1986, but we do have a few more of the modern ones. So here's examples of those QCs, what we were looking for. So at the top, I have digitizer noise. You can see just that really intense high frequency spiking. In the second panel, I have a triangular wave of non-seismic noise. We also have spiking in the third and fourth channel, what we're looking at. And then and the fifth channel, the particular is a nuclear event. But you see kind of right in the middle of that first arrival, we have a huge gap there. So we're looking for any kind of gaps like that. And we found about a third of that 108 events did have some kind of QC issue, at least one. 5 of them were enough that we did not include them into the data set. So while they had some QC issues, we did include them in the data set. There were only 5 that had some kind of timing issue. Whether or not that waveform was misattributed to an event or there was an actual timing issue is something that we have to look into further. So the second part of this is collapse data. And so we know that nuclear events can, when they're underground, they can create a cavity. That cavity then can collapse, and that collapse data is very important to understand from a source physics standpoint. This is something that Mike Passianos has a talk about on Thursday, so if you want to know more about collapses, please visit him. So we were given 52 digitized nuclear explosion events and their associated collapses. By given, I mean they were in a researcher's directory who has long since retired. So we have no known provenance. We don't understand if he's done any transformations to it. So my job here was to try to look at these collapses and understand whether or not they've had any transformations, if they've done any kind of, any transformations whatsoever to them, or if they are indeed the raw data. And so here again, I've kind of plotted up where these collapses are. Most of them tend to be on the eastern side of the site, and they are a much smaller time range from 79 to 83. So one of the problems that we ran into is we don't really have any ground truth. These collapses don't have anything in our database that we have that I can compare to. So what I did is, because each collapse had an associated main event, and we have some of these main events already that we've QC'd, I looked at that collapse, or the main event from my file and the main event from my database and compared the 2 waveforms. And as you can see here, the main event from my file is in red, the one from my database is in black. They don't match. They're close, they don't match. So what I did is I rotated it around 360 degrees and tried to see where I had the highest correlation coefficient. I took that correlation coefficient, rotated the seismogram, and find I do have a match. And as you can see, this one actually has a gap as well. So the other way I can look at some kind of quality control is by using moment tensors. I used a MT-INV, which is developed by Jean Ichinose. It's available online on SourceForge, I believe. So you could use this yourself. I assumed a pure negative isotropic collapse. I created that synthetic, and I compared it to my collapse waveforms. So as you can see in the east component, in that middle panel there, we have on the black, which is the real data, we have the highest amplitude positive, and if you look at the synthetic, our highest amplitude is negative. So most likely we have some kind of polarity reversal here. You'll also notice that it actually has some kind of timing issue. The synthetic arrives a little bit later, and that could be a timing issue in the station, but it could also be the fact that with these collapses, their origin time is not very well constrained. So that's not something I'm too worried about in this. I'm more concerned that there might be a polarity reversal here. So we can also use moment tensors to look at those real data as well, or the event data as well. I used a subset of moment tensors developed by Andrea Chang. In 2014, I generated those synthetics, and here I can look at to make sure we have the right polarity, to see if it has been transformed at all. I can try to look to see if there's any kind of amplitude issues, if we have the same order of magnitude for the most part. And so here you can see a really well matching event. This is Breton. And on all my 4 stations, for the most part, I have a really good match. I have some noise in the canab, but for the most part, it looks really great. So this is something that we can feel pretty confident about, that it hasn't been transformed. So just going further, what we want to do with this data, we're going to do a little bit more QC on it. We want to try and do some of the automated QC tools like Pycheron, which is available on GitHub. We are going to also try to investigate those timing anomalies with analyst picks and see if we can actually drill down to see whether they are timing anomalies or not. And then this data set is going to be released. This is something that we plan on releasing to the public. And then some other legacy stuff that I hope to talk about in September is some of our efforts with analog seismic, including microfiche or microfilm, as well as 9-track data, and all the wonderful problems that come along with that. And also we were looking at some of the ML techniques in order to not only expedite some of the digitization of analog film or analog media, but also some of these some of the metadata is handwritten on some of these canisters or papers inside of it, and we want to try to automate some of maybe that metadata collection to grab that metadata in a faster fashion to try to reduce the burden on ourselves. And so just in summary, we have about 108 events that we're going to release that are nuclear events from the LNN network. About 30% have some kind of QC issue that we've identified. We have about 52 collapse events with their associated nuclear events that we also identified and have used some sorts of moment tensors to try to confirm whether or not the researcher has done any kind of translations to this data. And we're also using the moment tensors for the known nuclear events to try to see if we do have any kind of rotations as well. And I guess with that, I'll have any questions.
Thank you very much. There is time for questions, so please. Please. Peter.
In the end, you mentioned some words about digitizer noise.
Mm-hmm.
Can you elaborate a bit on that? How large was that noise?
So as far as I understand, it's actually noise from the digitizer itself. This is before, yeah. So I don't know exactly how it comes about, but you can just see that it's like very high frequency spiking. It's very similar to the spiking.
Thank you. I don't see an online question again. Maybe more questions from the audience. Okay. Wonderful. Thank you very much. So then we turn to the last presentation in the session, Paul Richards. Yeah, I'm irritated about the time noted in the program here, but it is now your turn, and Paul Granston Richards is from the Lamont Doherty Earth Observatory. And your presentation is about the general discussion of analog seismic data and at last an origin time for the first nuclear explosion, TRINITY. Thank you very much for being here, and the floor is yours.
So please, can you call up the first slide? Thank you. And the second, showing my co-authors from, do I do this? Yes. So my co-authors are listed, please, on the next graph. Thank you. From, no, you went back.
Here's the next slide, sir. Mm-hmm. Big one.
So, of course, the first nuclear explosion took place in the United States during World War II. It was on July 16, 1945, before dawn in New Mexico. So, and it was a test of the implosion method for achieving a supercritical density of fissionable material. Estimates of the expected yield ranged from 0 to 50 kilotons. Nobody knew if it would work, but it did, and this became the weapon used against Nagasaki only 24 days later. This test was remarkable for many different reasons. Most obviously, because it changed the nature of warfare. We have not had World War for 78 years. But the prospect of one in the future is terrible to contemplate, as well as the main reason for us being here. The Trinity test was technically successful, but the fireball entrained the ground surface, and significant fallout made this the most significant radiation hazard of the Manhattan Project. For more detail, please download the blue-colored link and click on that link. Another detail is that there has been confusion on the origin time of this first nuclear explosion. It occurred before dawn that day in July 16, but when? This is terrible. Can you please have the next graphic? I will be describing two seismograms recorded at an Arizona station in Tucson, more than 400 kilometers to the west-southwest. The next slide. The Trinity nuclear explosion was done with the device in a sphere there being shown at the bottom of its 30-meter tower, but radio links to get accurate timing of the explosion failed on that day, and the formal report, the next please, simply gives these parameters: about 20 kilotons, listed as about 5:30 Mountain War time, and that time in the technical report on Trinity was given as some time within a 25-second window of uncertainty. So the next graphic, please, is the seismogram recorded for a period of about 5 minutes at Tucson. Do I have a pointer? No pointer. Yeah. So the 5 minutes are shown by those vertical columns, and after 15 minutes on a revolving drum, the next line is written. So in this seismogram, the ground motion at Tucson, most important are the two fastest waves to arrive. One is marked PN, and the time scale you can get is 60 seconds between the vertical columns, 1 minute on an analog recording. PN travels at about 8 kilometers a second along the top of the mantle. The largest signal we know today, modern notation, which came later, as PG. It travels essentially within the crust at roughly 6 kilometers a second, and then there are SN and LG waves and coda, but they can't easily be identified. So we can forget about them in this short talk. Next, please. 70 days earlier, in order to test the recording of the nuclear Trinity, was conducted a 100-ton trinitotoluene test at almost the same location. And here you see it with the people involved. It was seeded with radionuclides and so on. It was carried out very near the Trinity site, and being approximately 200 times smaller, the radio timing for this worked well. We have an absolute time for this event 70 days earlier. So I arranged with the US Geological Survey, the custodian of the Tucson analog records, to get the copy for May 7. And it turns out, with a very low amplitude, indeed, to have been faithfully recorded by the same system that recorded nuclear Trinity on a classic short period Benioff of the 1930s. So we would expect a signal on the order of 100 times smaller, and indeed that turned out to be the case. If you take the biggest part of the Trinity signal and scale it down, you get about the size of the trace itself, the thickness of the trace, a very small amplitude, and I'll show it shortly. Please, the next picture. This is an aerial view of the two explosions taken 28 hours after nuclear Trinity. The upper circle is the nuclear one, and about 700 700 meters, more or less to the south and slightly east, is the trace, the damage to the vegetation apparent from the chemical one, for which we have an accurate time. And it's nice to see that perpendicular to that in the direction towards Tucson, it's the same distance. Please, the next graph shows my most technical slide, and let's describe it from the bottom to the top. On the bottom is shown that feeble analog record of the chemical explosion, shown for a little bit more than a minute. And those wiggles are the PG arrival at Tucson, for which we know the absolute origin time. The line above it shows a filtered. So the bottom line was scanned at 1,000 dots per inch, digitized by software from Miyake Ishii, digit size. Then from then on, it's a digital analysis, and we can apply modern methods. You see a window for about 20 seconds, passed in the band from 1 to 10 hertz. The 1/3 up from the bottom is the TRINITY recording with an unknown origin time, and it becomes a cross-correlation method of aligning those two signals, which is done very satisfactorily in the top line. And mostly with my colleagues, I write modern papers on modern methods of analysis, and from millions of cross-correlations, we have that experience of saying when we're satisfied that the cross-correlation is a faithful alignment of two similar signals. And out of this, we can then transfer the known origin time for the chemical record to the known seismogram of the TRINITY record, and you see there that estimate of 1129 point approximately 24 seconds for the TRINITY origin time. So next, please, the graphic is our summary. Radio timing failed for the TRINITY origin time, it's unknown. A scan and digitization for both events was successful, and you see our conclusion. Now, it's somewhat unfortunate that in the official list of basic parameters of nuclear test explosions, the origin time for TRINITY is given as 12:29 GMT, which is the wrong hour, as well as the wrong tens of seconds, or certainly the wrong second. The official time would give that test as having occurred after dawn in New Mexico, so it must be wrong. I said that the official report from the TRINITY technical summary, written in the 1940s, was listed as 5:29 Mountain Wartime. Perhaps not known to the official record keepers, Mountain Wartime throughout World War II in New Mexico was actually what today we know as Mountain Daylight Time. If you incorrectly interpret Mountain Wartime as Mountain Standard Time, you would get the official reported hour, which I believe to be wrong. It turns out then that Mountain Daylight Time is 6 hours away from GMT, and so it should be 11:29 GMT to the nearest minute, and then we believe that the and my final graphic, please. What are the main messages to say here? Frankly, who cares what the exact origin time was of TRINITY? The fact that it was here or there, a few tens of seconds, it's embarrassing to have an hour wrong, but a few tens of seconds, who cares? Well, that's not the main point. The main point is that with high-quality analog recording and careful scanning and a good digitization system, the whole panoply of modern seismogram analysis of digital data with cross-correlation as the principal tool is available to do all the good things that are being done today with digital data applied going back decades into the analog era. It is my belief that from low-quality stations, there's not the greatest need to preserve analog data, but for high quality stations which were used by researchers of their day as their principal professional platform, it is so important to preserve that data, not only for very important activities of Homo sapiens, such as the first nuclear explosion, of course, for the multi-megaton explosions, for which today there is no military reason, but which were faithfully recorded by global networks in the 1950s and the 1960s, and were documenting phenomena that, let us hope, will never be seen on our planet again. It's so important to preserve those data for future generations. And so that is my last two lines. Modern methods of cross-correlation analysis can be effective in application to scanned, digitized, high-quality old records. Thank you for your attention.